Hello, we are group number 9, and our project is about a design and techno-economic analysis of a combined heat and power plant using African palm residues as an energy source. To develop this project, we consider some factors. As we can see, we have location, equipment, energy, economy, and safety. But firstly, we have to know what is a cogeneration system, and it is a simultaneous production of mechanical energy or electricity and heat from a single fuel source. And also the waste heat from power generation is used for heating. In this case, our goal is to produce at least 5 megawatts of energy. As I mentioned, we use African palm residues as an energy source. And in this case, we can see that the palm tree has 10% of oil and 90% of biomass. And also we have 5 different kind of residues. We have empty fruit bunch, kernel shell, kernel cake, oil palm fiber, and palm. And also it's important to recognize the advantages of using this kind of biomass as a fuel. We have a high energy efficiency, primary energy savings, and emission reduction. And also it helps to reduce coal consumption. Regarding the location, we know that Ecuador is located in the 7th position in the world in the African palm plantation. And also we can find this kind of palms in the west, in the Pacific coastal plain, and the lower foothills of Los Andes. But the best place we could choose was Quininde, and it is located in Esmeraldas. Its annual production of African palm represents 27% of the national production. Its temperature is about 23 degrees Celsius, and the pressure is 1,014 hectopascals. And also we know that it has the best lands for agriculture due to the large number of surrounding rivers.
Now we are going to talk about the general process description. Okay, this is our block diagram, which starts with the raw biomass selection. In this case, we are using the oil palm mesocarp fiber and its kernel shell. And then this biomass passes through a mechanical pretreatment, which gives us a determined composition of carbon, hydrogen, oxygen, and nitrogen before it's combusted. And then we have the cogeneration process. We can see the outlet streams like exhaust gases, wastes, and our two main products, which are steam and electricity. Okay, so here we have the inlet streams composition. In the first one, we have the mesocarp fiber, and in the second one, we have the kernel shell. The calorific values are shown as the other conditions like temperature and pressure, which are at environmental conditions. In this case, we use 600 kilograms per second of each type of biomass as mass flows. We also have the air flow used for the combustion and the water flow for steam production. Okay, so now we have a more detailed process description including the equipment. For the equipment, we include one mixer, 4 heat exchangers, 2 pumps, a reactor, and a turbine. First, we must segment the process in 2 routes, one for the combustion gases and the other one for the inlet water. So, it begins with the mixture of the 2 types of biomasses inside the mixer, and then this mixture is going to be preheated to 250 degrees before it enters into the reactor. We also have an airflow to start the reaction, and then when the reaction is ended, before the gases go through the atmosphere, this heat is used to evaporate the inlet water to produce steam. And it is important to mention that the water had been pumped before it evaporates. And then this vapor steam is going to move the blades of the turbine to produce work, and it also could be used for heating another process. Okay, now we're going to talk about the simulation description. To choose the more suitable thermodynamic method, we use a decision tree, which involves the nature of the components, like if it is polar or non-polar, or if it is electrolytic or not, the pressure, for example, if it has a liquid-liquid equilibrium. So by following this tree, we choose swap Redlich pump for combustion gases and NRTL for water. Next, please. Before doing the simulation, we made some assumptions. First, the type of boiler that we select was the tube water boiler because it is the most used at the thermoelectric plants to produce energy. And then to simulate this water tube boiler, we used a reactor plus a heat exchanger. We assume that there are no ashes as wasted in the simulation. And for the centrifugal pump, we chose an efficiency of 75%. For the turbine, we assume an 80%. For heat exchangers, we select carbon steel as the material of construction and a shell tube type exchangers with a countercurrent configuration. And you can see this is the simulation that we made using the Software Pro tool.
About the results, we had a total work of 6,930 kilowatts, and we had a 424 total thermal production, and about boiler energy, we had 11,280 kilowatts. And finally, we had a 65% of efficiency. About the process control loop, we have a PID feedback control for the evaporator. This control is posed for the exhaust outlet temperature. This is a process variable that is measured to compare it with the expected set point.
So now I'm going to explain about the techno-economic analysis. The cost and the cost flow diagram and value were obtained using that cost. Here we can see the capital and operation expenditure, the land factor technique, the equipment cost. What are the equipment are going to use in this process? The equipment are going to use in this process are 2 pumps, 1 reactor, 1 storage tank, 1 turbine, and 4 heat exchanger. What are the equipment costs in this process? The equipment cost in this process is $8.6 million. The delivery cost is $434,000. The land factor was obtained using CAD cost is 4.74, and the fixed capital investment is $15.7 million. So it's important to know the direct manufacturing cost, the fixed manufacturing cost, and the general cost. For the direct manufacturing cost, we consider raw material, operation staff, utility, and all of these points that you can see here in this table. For the raw material cost, we have mesocarp fiber, kernel shell, and water. For the operation staff, we consider 48 operators are going to work. The total direct manufacturing cost is $7.5 million. So for the fixed manufacturing cost, we consider a value of $5.0 million. The fixed manufacturing cost is $8.7 million, and the general cost is $507,000.
Process safety and environmental protection. For safety and efficiency of the pilot plant for cogeneration of energy, it's necessary to consider the possible dangers that may arise for which certain specification and regulation must be considered, such as the expulsion of combustion gases, temperature, composition, among other important aspects that guarantee the safety of working personnel and the environment. During the cogeneration process in a pilot plant, there are different types of risks that can cause problems for the working personnel. It is necessary to identify them and be aware of the possible safety problem that can occur in the plant to avoid disaster in the cogeneration of energy. To avoid some of the possible dangers present in a cogeneration power plant, periodically it is necessary to carry out an evolution to the pressure, temperature, and flow indicators, safety valves, boilers, tanks, and corrosion control to protect industrial safety. Personnel should wear heat-resistant gloves and protective goggles to prevent any substance from entering the eyes. Ear protectors should be worn to protect the hearing. Helmets, boots, and overalls must be worn. For emergency control, full protective clothing should be worn, including safety goggles, gloves, and vapor respirator. Safety and environmental impact. In the country, there are little more than 257,000 hectares of oil palm, and if we talk about the deforestation of African palm in Ecuador, the province of Esmeralda occupies the first place, reaching a total of 45% of the total of this resource. The main problem in Ecuador is precisely deforestation, and 90% of the deforestation is due to the exploitation of agricultural resources due to human malpractice. For that reason, it is necessary that the residue of the African palm has an added value and can be used in this entirety, reducing the impact by generating energy and allowing this balance with the environment. This project will evaluate the feasibility of generating energy from African palm residues following the environmental regulation that allow its adequate exploitation while preserving the environment. Conclusions. African palm grains in Ecuador does not have a total value and is generally discarded, which generates a great negative impact on the environment. We obtain an efficiency of 68%. This means that of all the raw material entered, it is possible to take advantage of this percent for the generation of things that can be used for another industrial process or energy production. Through the cost tool, the profitability of the process was evidenced, and that is also within the first 3 years, with an annual interest of the General State Bank of 12% and a payment of 22% of taxes. These are the references that we use to make the project. Thank you.